All right, so this is Unit 3, Worksheet 2, Self-Driving Car. And the problem we're trying to solve is that while cruising along a dark stretch of highway with the cruise control set at 25 meters per second, you see at the fringes of your headlights that a bridge has been washed out. You apply the brakes and come to a stop in 4.0 seconds. Assume the clock starts the instant you hit the brakes. And so first we're going to go ahead and construct a qualitative motion map that represents the motion described. And so what we see is we are going at 25 meters per second, and we are going to apply our brakes and come to a stop. So that means that this motion for us is going to be slowing down. And the time that it takes for us to do that would be 4 seconds. And so that means our time from start to end is going to be 4.0 seconds, and that's our delta t. So to construct our motion map, we are going to maybe assume that we start at 0, we start timing, and we'll just call wherever we start braking 0 meters. Okay, so this is our, and we are going to just draw a qualitative motion map. That means we are not going to have numbers. So we'll just go ahead and go at 0 seconds, we'll be there. Maybe 1 is going to be a little bit shorter, 2 is going to be shorter than that, and 3 is going to be shorter, and then we have 4. Okay. And then our acceleration arrows, we'll do that in a second. All right, so we're still drawing qualitative graphical representations. So that means whatever we draw is just going to be qualitative, okay? And so slowing down, starting at 0 is going to start like that. Okay, so our tangent lines here are getting flatter. So we have a very steep one here. And we'll see that our tangent lines are getting flatter and flatter as we go up in position. So then that means that it is slowing down in the positive direction for this graph. Next, I saw a lot of people draw something like this. So this means that you start off at a high velocity or a non-zero velocity and end at 0. And because our slope is a negative slope here, that means our acceleration graph is also going to show a negative number. All right. So this is our first page. And now we're going to draw our acceleration arrows back to our motion maps. And we had a negative acceleration, so we're going to show negative acceleration vectors. Okay, and they should all be approximately the same size. Looks like mine just got longer, but they should be the same size. Okay. And now we're going to look at this page. So we're going to construct a quantitative graph. And so we know that our initial velocity is about 25 meters per second. And our final velocity is 0 meters per second. That means our delta V is just 0 meters per second minus 25, or we'll do that part later. Okay. So I think during class, people mentioned that they wanted to go up by 5s. So this is 5, 10, 15, 20, 25, and we'll go 0, 1, 2, 3, 4, 5. Okay. And actually, I changed my mind. I would like to go up by 10s instead of 5s. Okay. So we have 25 seconds is where we started. So it's going to be the halfway point here, and we ended at 4 seconds. All right, so we have 25 to 4. And so we're going to quantitatively accurate versus a v velocity versus time. And now we're going to show the displacement. And so during class, we talked about how the displacement is really this area under the graph. Okay, so before we were drawing displacement for constant velocity when it was the flat, and now there's a slant. And so the area under the graph, since this is a triangle, is going to be delta x is going to be 1/2 base times height. In this case, our base times height is called velocity times delta t. All right, and so the height of our triangle, so we're going to go delta x is equal to 1/2. The height of our triangle is 25. So we're going to have 25 meters per second times the delta t, which is 4 seconds. And we're going to do 1/2 times 25 times 4, and we know that 1/2, these cancel out. We have 100 meters is going to be 50 meters. So our delta x here is 50 meters. Okay, using the graphical representation to determine how far the car traveled. So that's our delta x, right? We'll just go ahead and move this over here. So, and our work is shown. So again, the area of a triangle is going to be 1/2 base times height. And the area of our triangle in this case is called delta x. And our base will be delta t, or velocity, and our height will be velocity or delta t, depending on what number you use for which. All right, so we have 1/2 25 meters per second times our time, which is 4 seconds, and that's going to equal 50 meters. Okay. In order to draw the acceleration time graph, you're going to need to determine the car's acceleration. So we are going to work out our acceleration, which is delta v over delta t. And our acceleration is 25 meters per second over 4 seconds, which is going to give us, actually, this is where delta v comes in. So that's going to be final velocity minus initial velocity over final time minus initial time. And let me just go ahead and write that out over here too. So that's going to be 0 meters per second minus 25 meters per second over 4 seconds minus 0 seconds. And so that means it's going to be negative 25 meters per second over 4 seconds, which is going to be negative 6.25 meters per second per second. So again, that's going to be, so if we go by threes, it's going to be very close to the 6. And so we have, this is our acceleration. All right, and that is the second page of our worksheet. And now we're going to go to the third page. So we have a car traveling down the highway at 35 meters per second, and it's able to accelerate at a maximum of negative, right, because we're slowing down, negative 7 meters per second when applying the brakes. So we're going to draw a qualitative velocity versus time graph. And so that means, again, it's going to have a high velocity, then goes down to 0 after some time. Okay. What information do we need to determine minimum stopping distance? And so the information that we needed is going to be, this is our minimum stopping distance. And this, everything in this area. All right, so that's our delta x, which is our minimum stopping distance. Okay, so our equation in this case is 1/2 velocity times delta t. So we need velocity, and we need to know the delta t. So we need to know the change in time. And so now we're going to draw the quantitative version. All right, and so our car was traveling down the highway at 35 meters per second. So I think I'm going to choose to go by tens again. And I'll go by ones. 1, 2, 3, 4, 5, 6. Okay. And in our problem, we have the car traveling at 35 meters per second. So it's going to be the halfway point between 30 and 40. And it's going to, we don't have the delta t. So to find out what the delta t is, I think what I'm going to have to do is use the acceleration equation. So I know that the acceleration equation is delta v over delta t. And the delta v is going to be negative 35 over the change in time. And we don't know what that is, but we do know that acceleration is negative 7 meters per second per second. So if we go down negative 7, starting at 35, we're going to end up at 5. Okay, so 35 divided by 7 is going to give us 5. And so our delta t is basically going to be acceleration over delta v. And so we're going to take that equation and isolate for delta t. Okay, so we have negative 35 meters per second over negative 7 meters. Sorry, got ahead of myself there. So negative 35 meters per second over negative 7 meters per second, we have 5 seconds. And so that's where our delta t is. And so we weren't given the time, and but we did have enough information. So we had acceleration, right? We also had the change in velocity. And now we can solve for, so now that we had velocity, we didn't have the time. And so now we can go back with our information and solve for delta x. And so our change in velocity was negative 35 meters per second times our time, which was 5 seconds. Okay. And so we have 35 times 5 is going to be 175 meters, because the seconds end up canceling to 1. And we have 1/2. So 1/2 times 175 is going to give us 87.5 meters. And so this area under the graph. Okay, so this area right here, this represents 87.5 meters. So our delta x, which represents 87.5 meters. That means from when the car started braking all the way when it reached a stop, it took the car 87.5 meters to come to complete stop. All right. And so now let's take a look at number 10. What would change about your answer if the same car was moving at 40 meters per second? So at 40 meters per second, let me choose a different color. Okay, so we have 40 meters per second right here. So that means that the car with the same slope is going to be about that much. Okay. And if it was 30 meters per second, then we're going to have a car that reaches about that much, right? So the acceleration continues to be negative 7 meters per second, but then we see our lines change. So I saw that at 30 meters per second, then our delta x becomes this area, and it's slightly smaller than when it was at 35 meters per second. And now our area for 40 meters per second becomes all of this area right here, okay? And that's a lot larger than the green section, which was at 30 meters per second, and the orange section. All right, and so that is the first 3 pages of Self-Driving Car. And we will work out the code when we get there.